All right, we are up to lesson 4. Again, no new lesson notes, so we're going to get right into the examples. In 1990, Nigeria had a population of about 95.3 million. By 2000, the population had increased by about 28.4%. During that decade, the population can be adequately modeled by an exponential function. Use the exponential growth and decay formula to solve the following. So number 1, find the growth factor per decade. So 28, it's going up by 28.4% per decade. So I know that 28.4% is 0.284. And because it's growth, my growth factor is going to be 1 plus the percentage. So 1 plus 0.284. So my growth factor per decade is 1.284. So that is your answer to number 1. Number 2, express the population P of X in millions of people as a function of time X in decades since 1990. So if we use my formula, okay, what is my initial value? My initial value is 95.3 million. So I'm going to use 95.3 as my initial value, with the understanding that that does not mean 95.3 people. It means 95.3 million people. So 95.3 times my growth factor, we said, was already 1.284. That was my answer from number 1 to the power of X. So 95.3 times 1.284 to the power of X. That is my equation. The understanding is that the X value here is not years. The X value is number of decades. So the X value in this case is number of decades. So that is your answer to number 2. Okay. Number 3, calculate the population of Nigeria in 1996. So 1996 is 6 years later, 6 years after 1990. So that is 6 years later. I need to convert that to decades, because if I plug in X equals 6, that's going to mean the population 6 decades later, not 6 years later. So just like in the previous lesson, how do I convert years to decades? I either have to multiply by 10 or divide by 10. In this case, I have to divide by 10. Okay? Because 20 years, if I divide that by 10, is 20 divided by 10, which is 2 decades. 30 years, 30 divided by 10, that's 3 decades. So 6 years, 6 divided by 10 is 0.6 decades. So I'm going to, in my equation, I'm going to plug in 0.6 for X. So 95.3 times 1.284 to the power of 0.6. And whatever that answer is, that is going to tell me the population of Nigeria in 1996. So let's calculate that. So let's go to Desmos. So 95.3 times 1.284 to the power of 0.6. So that rounds to 110.7. So that doesn't mean 110.7 people. That means 110.7 million people. So the population in 1996 is 110.7 million. Okay. Number 4, rewrite the equation as P of T, where T represents the amount of time in years after 1990. So the way I have the equation written currently is that the X value is the number of decades. So now I'm going to rewrite it. I'm going to rewrite it such that the variable does not represent decades, it represents years. So the question is, how do I go from years to decades? Well, I figured out in number 3, if I take the number of years and I divide it by 10, that will give me the number of decades. So in this case, to convert from years to decades, I have to take the number of years and divide it by 10. So how is that going to work in terms of the equation? It's going to be 95.3 times 1.284 to the power of, and what variable did they say to use? They said to use t. So 1.284 to the power of t over 10. T divided by 10. Because if I take the number of years and divide it by 10, that will give me the number of decades. So this is my equation where t represents the time in years. So t, in this case, means years. So number 5, based on your equation, what appears to be the growth factor per decade? So to figure that out, to figure out the growth factor per decade, okay, I am going to have to do some algebra here. Now I want you to watch what I do. I'm going to take my equation from number 4 and I'm going to rewrite it like this. So 1. So look at what I did here. The 95.3, that stayed the same. The 1.284, that stayed the same. But look at what I did here. I took t divided by 10. I took t over 10 and I rewrote it as 1/10 times t. Is 1/10 times t equal to t over 10? And the answer is yes. So is what I did here mathematically legal, as I like to say? Yes. Okay, because 1/10 times t is equivalent to t over 10. The reason why I break it down like this, the reason why I take the t over 10 and break it down into 1/10 times t is that now this number that's in the parentheses is now my growth factor per year. So that is your answer. The growth factor per year is going to be 1.284 to the power of 1/10. That is your answer to number 5. And I got that by simply breaking down the t over 10 into 1/10 times t. Okay, let's go ahead and go to the second set of examples here. So number 6. In healthy adults, caffeine has an average half-life of 6 hours. Okay, that means that the amount of caffeine decreases by 50% every 6 hours. A person drinks a cup of coffee containing 100 milligrams of caffeine at noon. Each of the following expressions describes the amount of caffeine in the body predicted by an exponential model at some point after consumption. Okay, how many hours after consumption? Well, if I were to write an equation, it would be 100, because that's my initial value. My decay factor would be 0.5 because it's a half-life to the power of x. Now, in this case, the half-life is 6 hours. The half-life is 6 hours, which means that my x value here doesn't represent the number of hours. The x value here represents the number of 6-hour time periods. So plugging in x equals 1 really means 6 hours. Okay? Plugging in x equals 2 really means 12 hours, so on and so forth. So I actually already answered part A. This expression represents the amount of caffeine left after one 6-hour time period. So part A is 6 hours. Okay. Plugging in x equals 3 means 3 6-hour time periods. So that means 18 hours. Okay. Plugging in a half for x means a half of a 6-hour time period. So that would be 3 hours. Okay. Plugging in 5/6 for x would mean 5/6 of a 6-hour time period. Well, what is 5/6 of 6 hours? That's 5 hours. Okay. So the key is, again, to remember that in this case, just like in this first setup here, where x represented decades, down here, x represents the number of 6-hour time periods. So number 7, I'm going to do down here, write an expression to represent the amount of caffeine left in the body after 4 hours. So I have to convert 4 hours to the number, so 4 hours, okay? In order to convert that to number of 6-hour time periods, I have to divide that by 6. 4/6. Okay? 4/6 6-hour time periods. Okay? So I have to divide it by 6, just like up here, I had to divide the number of years by 10. Okay, when I was up here, I had to divide the number of years by 10 to convert to decades. In this case, I have to divide the number of hours by 6. So I'm going to plug in 4/6 for x. So the expression is going to be 100 times 0.5 to the power of 4/6. Okay. Number 8. Write an expression to represent the amount of caffeine left in the body after H hours. So the key is to figure out what I plug in for x. I have to take the number of hours and divide it by 6. So up here, when it was 6 hours, 6 divided by 6 is 1. When it was 18 hours, 18 divided by 6 is 3, so 3 was my x value. Okay. Down here, when it was 4 hours, I had to divide 4 by 6, and that was the value that I plugged in for x. So again, I'm taking the number of hours and dividing it by 6. So my expression is going to look like this. It's going to look like 100 times 0.5 to the power, I think it says to use h, right? So to the power of h over 6. If I divide h by 6, the number of hours by 6, that will mesh with this where x is the number of 6-hour time periods. So 100 times 0.5 to the power of h over 6, where h is now the number of hours. Okay. Last question, number 9. Using your expression, what appears to be the decay factor per hour? So to do that, I'm going to play the same game that I played up here with this. So I'm going to take my expression, 100 times 0.5 to the power of h over 6, and I'm going to rewrite it like this. So remember, up here, I took t over 10 and I broke it down into 1/10 times t. Where here, I'm going to take h over 6, and I'm going to break that down into 1/6 times h. Okay? Once I break that down, whatever is inside the parentheses, that is now your decay factor per hour. So the answer to number 9 is 0.5 to the power of 1/6. Okay? The good thing about this is it doesn't matter what the half-life is, this pattern would hold true. So if the half-life were, for example, 7 hours, it would be 0.5 to the power of 1/7. If the half-life were 15 hours, it would be 0.5 to the power of 1 over 15. So that pattern holds true. The key is taking this fraction, all right, up here it was t over 10, and breaking that down into 1/10 times t, or in this case, taking h over 6 and breaking that down into 1/6 times h. That is the key when you're finding your different growth and decay factors here. And that is it for this lesson.